I said this was what we call a Radian measure result, right? So at last, I'm going to have a starting point that is not some random thing like, hey, look at this inequality. Why is it true? I don't know. This is where textbooks begin because you guys know Radian measure. You know results for geometry, that kind of thing. So I'm interested in three particular shapes here, okay? Number one, I'm interested in this triangle OAB. Triangle OAB, okay? Then I'm interested in sector OAB, so the slice of pizza, okay? And then lastly, I'm interested in the bigger triangle here, triangle OAT, okay? OAT. I called it T because I've got a tangent going through here. And believe it or not, this is where actually you're like, sine just means curvy, cosine means complement of the curvy thing. Tan, why is it called tan? Tangent, what does that have to do with tangents? This is what has to do with tangents, okay? So watch, it'll come out. This triangle here is formed off the tangent from this radius, okay? And there's my radius R here and here, all right? Now, remember I told you? I'm interested in all of these three shapes, okay? So can we work out each of their areas? That's what I'm after, okay? So I've got an angle in here, X. And as before, I'm considering it just as an acute angle. Okay, so 0 less than x less than pi on 2. Okay, there's my domain. So can we work out what these areas are? Let's try the first one. The area of triangle OAB. Well, I've got two side lengths and I've got an angle. So which way should I get its area? Half AB sine C, right? Which in this case, A and B are both the radii, and the included angle I'm after is the x, okay? So half AB becomes half R squared, and sine C becomes sine x. Ta-da! Okay, now I'm after the area of this sector, OAB. Okay? And again, this is just a standard radian measure result, right? Area of a sector is half R squared theta, which in this case is just x. Okay. Alright, now lastly, this is like a little extra work, but not that much. What's the area of this bigger triangle? Area of triangle OAT, or tau, if you like, whatever, okay. What's its area? Well, here it's not quite so simple. I need to know, well, I've got one side length, R. I also know that this is a right angle here, there, okay. So, what should I do? I probably need, like, you know, base and height, right? Because I've already got height here. That's just the perpendicular height. So how will I work out this base here, AT? How would you go about doing it? This actually is a little bit like when I asked you to prove sine, the expansions for sine A plus B and cos A plus B. And I said, find the lengths of these sides in terms of trigonometric functions. Right now, think about this. I've got this side R. I know this angle X. And I'm trying to work out AT. The ratio I'm after that relates this side, and that angle is opposite on adjacent, right? Which is tan. Okay. So therefore, tan x.
This is all getting recorded.
Tan x is equal to opposite on adjacent, AT on R. Okay. So therefore, the actual length I'm after is R tan x. Happy? Okay. So I've got that distance down here. Now the area of a triangle is half base times height. Right? There's my base, there's my height. So the area is half R squared tan x. I've got my onto at the front. Is that okay? Alright, now can you see why I brought out this result? Okay? And think about it in connection for what I'm trying to prove. Have a look at these three shapes. Number one, the small triangle. Number two, the sector. Number three, this bigger triangle that forms off the tangent. Okay. No matter where you move the T, okay, suppose I move it, let's draw another circle. And here I've got the center, and I'm going to move, the T used to be over here, so I'm going to move it closer, somewhere like there, okay? And then I draw that tangent, draw that, there you go. There's another version of this, but it's smaller, okay? Those three shapes, 1, 2, 3, will always be, this is always smaller than that, this is always smaller than that, right? So, I would write that as area of OAB is always less than the sector that's around it. And the area of this sector is always smaller than the area of the triangle formed around it by the tangent, which is the O triangle, right? Come in. Okay, sports cancelled, you already knew that. Year 11 students who returned a wet weather permission note. You can go home. And there's a list here of people who haven't. This is tricky because there are 2 of you and it doesn't say which one it is.
I'm up in English.
Please tell me I'm not on that list.
No, no one else is on the list.
Yes.
So.
But if we just go home, that won't know.
Wait, so it's one of the vector views.
It's one of the, yeah.
No,
that's
you
right.
have to go to them and they give you
I'm
what's
pretty sure the other one.
Yeah, I reckon the other
Yeah,
one
it's
too.
only have you opened it?
Okay, we're almost done.
I
Stay with me, people. Stay with me. Stay with me.
Yeah.
Okay, let's just sub it in. Okay. Half r squared. Sine. Right? Half r squared x. Half r squared tan. Divide everything through. Oh snap. Okay. So now, let's replay it again. Okay, the textbook begins and it says, there is a circle. And you're like, what does this have to do with calculus again? Okay, and they're like, just wait, I'll get there eventually. In like 2 hours, okay? They go, they prove this inequality. Then they use this inequality to prove this limit. Right? And then they use this limit so they can simplify first principles for limit as h approaches 0 of, sine x plus h blah blah blah. And then at long last we get to the derivative of sine being cos. And then you get everything else from that, which we already saw yesterday. Okay? Exhale. That was it. Okay? Now like I said, this proof, okay? I'm not showing you this proof because you must reproduce it. Like section E, or actually it's not section E anymore, it'd be like question 4 or something like that. It's just prove the derivative of sine x from like first, really super first principles, okay? They're never going to ask you to prove that. However, you think about what all of this is. There was, this is radian measure, okay? Then you've got limits, then you've got trig expansions, then you've got limits again. All of that stuff you do need to know, okay? So all the pieces of this you must understand. One more thing, and this is actually an important bit. When you are thinking about where all of this came from, okay? Maybe this seems normal to you, but didn't to me. When you're differentiating trig functions, everything must be in radians. Okay? Now, I'd actually like you, get a red pen out, get a red pen out, okay? And I want you to write this because this is crucial, okay? This is going to come back and bite you. Everything to do with trig and calculus. Differentiating, later on we're going to learn integration as well, whatever that means, okay? All of it must be in radians. Now, that seems weird because you're like, radians, degrees, it's just a measurement thing, right? It's just units. Like if I said to you, tell me how tall I am in centimeters. Or work out my BMI, in centimeters, use meters, whatever. You'd be like, it's no problem. I can use whichever units I want, right? Now, why can't I just use whatever units I want? The reason I can't use whatever units I want is because this whole result, particularly this part and this part, they do not make sense if you do them in degrees. These are radian measure results, right? If you plug in degrees here, things are going to break down. Actually, it's more so this one, right? So, when you're coming back to differentiating, and I'm going to do it all in radians, and I'm doing integration, and I'm only doing it in radians, you're like, why is that? It's because where it all started was radian measure, okay? Does that make sense? It's going to come back and it'll be very important, so just keep that.